Welcome back, everyone. Okay, today we're diving into a highly focused, kind of forensic crash course into the mechanisms, the metrics, and the math of water pollution. We're going to literally take an entire chapter's worth of environmental engineering and break it down into clear, actionable pieces so you can truly master how scientists track, measure, and calculate contamination. Let's get right into it. But before we get into all the formulas, we really need to look at the real-world crime scene. Just take a look at the reality of India's severe water crisis. We're looking at reports showing a staggering 80% of surface water is polluted, mostly by untreated domestic sewage. And because of that, an estimated 600 million people are facing high to extreme water stress. That's a massive, massive number. Understanding the science behind these numbers is absolutely crucial if we're going to actually address this crisis. So, here's our game plan for today. We're looking at the reality of water pollution, defining our contaminants, comparing fund versus stock pollutants, measuring oxygen demand, calculating code, and wrapping up with physical quality parameters. All right, part 1, the reality of water pollution. Now, here is the absolute foundational definition that you need to lock in. Water pollution is, quote, the loss of any of the actual or potential beneficial uses of water caused by any change in its composition due to human activity. Notice the emphasis there. While nature definitely has its own cycles, it's human activity, our actions, that really act as the main catalyst, pushing contaminants into the environment in excess. And that's what ultimately robs the water of its beneficial uses. Moving on to part 2, defining contaminants. So where is all this coming from? Well, we categorize these sources into 2 main suspects. First up is the point source. Think of this as a single, large, clearly identifiable source, like a factory pipe dumping straight into a river. You can literally point right at it. On the flip side, we have the non-point source. This is diffuse pollution. You can't trace it back to one single physical spot. We're talking about general sediment runoff, pesticide spraying, or fertilizers just washing off massive agricultural farms after a rainstorm. And this brilliantly illustrates exactly how that plays out in a real river system. Over on the right, you see that factory with a pipe discharging directly into the water. Boom, textbook point source. But trace those other arrows coming from the cropland, the rural homes, the city streets. Those are your non-point sources. They're seeping into the river system across huge, unspecific areas. And honestly, that makes them incredibly difficult to track and control, compared to just plugging up a single factory pipe. Which brings us to part 3, fund versus stock pollutants. Now this right here is a real game changer in environmental science. We divide pollutants into 2 categories based on how the environment handles them: fund and stock. Fund pollutants, the environment actually has some absorptive capacity for these. Given enough time, things like degradable organic wastes, thermal heat, or eutrophic nutrients can actually be broken down or processed by natural bacteria. But stock pollutants, well, they are a totally different beast. The environment has basically zero absorptive capacity for these guys. We're talking persistent synthetic chemicals, heavy metals like lead and mercury, and non-biodegradable plastics. They don't just go away. They accumulate permanently, compounding over time, kind of like an unpayable debt. Just to put that into perspective, a single plastic bottle acts as a stock pollutant for over 450 years. Crazy, right? So when we break down these biological and chemical threats, we see some usual suspects. Under infectious agents, we've got bacteria and viruses, mostly stemming from human and animal waste. Then there is oxygen-demanding wastes, stuff like biodegradable animal waste from sewage and feedlots. Next, we see plant nutrients, like nitrates and phosphates. These largely come from fertilizers, and they're what cause that massive, excessive algae growth you sometimes see on lakes. And finally, those highly dangerous stock pollutants we just talked about, heavy metals, things like lead, mercury, and arsenic, usually seeping in from unlined landfills or industrial discharges. All right, part 4, measuring oxygen demand. 5 milligrams per liter. Okay, I really want you to sear this exact number into your memory. This is the absolutely critical threshold for dissolved oxygen, or DO, in water. DO is just a measure of the gaseous oxygen dissolved in the water. Now, if those dissolved oxygen levels drop below 5 milligrams per liter, aquatic life is immediately put under severe stress, and they will actually suffocate. So measuring oxygen demand is really all about acting like a detective and figuring out exactly what is stripping this life-saving gas right out of the water. And the most widely used traditional forensic tool to figure that out is BOD, or biochemical oxygen demand.
specifically BOD5. What this test does is establish the concentration of organic matter by measuring how much dissolved oxygen microorganisms consume to stabilize that waste. Why the 5? Well, it's called BOD5 because scientists accurately measure the dissolved oxygen at the very beginning and then again at the end of a strict 5-day period. During that time, the sample is incubated in total darkness at exactly 20 degrees Celsius. It's essentially sending the bacteria on a very strict 5-day working vacation.
Let's move to Part 5, calculating COD. Now, chemical oxygen demand, or COD, measures the pollution potential of organic matter through chemical oxidation rather than biological breakdown. And here's the formula. Now, I know it might look a bit intimidating at first glance, but I promise you it's actually super straightforward once you break it down. COD equals the volume used in your blank sample minus the test sample. You multiply that by a series of constants, 0.1 times 8 times 1,000 times 100, and then you divide that whole shebang by the total volume of the sample. That's it. Let's actually apply this right now to solve a real-world problem.
Okay, so the crucial point is extracting the right data. Here are the parameters given for some industrial wastewater. Let's see. The sample was diluted 100 times. We used a 0.1 normal ferrous ammonium sulfate solution. The volume consumed was 5 milliliters for our blank sample and 3.5 milliliters for our test sample. And finally, a 10 milliliter sample volume was used for the overall estimation. Great. We have literally everything we need.
So let's just execute the math step by step. Step 1. Identify our given variables. The blank is 5, the test is 3.5, and the volume is 10. Step 2. Let's plug those numbers straight into the top half, the numerator of our formula. So 5 minus 3.5 gives us 1.5. We multiply that by 0.1 times 8 times 1,000 times our dilution factor of 100. Grab a calculator, and that gives us 120,000 in the numerator. Step 3. Simply divide that by our sample volume, which is 10. And boom, there you have it. The COD is 12,000 milligrams per liter. See, I told you, complex environmental engineering math is totally manageable when you just organize your data. Finally, Part 6, physical quality parameters. When you're in the lab, testing for solid pollution is really all about hitting specific temperature and filtration thresholds. First up is total solids, or TS. This is simply the residue left over after you evaporate and dry the water sample at around 103 to 105 degrees Celsius. Now, if we crank that heat way up to 500 degrees, a lot of those solids will literally burn off, and that portion is your total volatile solids. But what about whatever actually survives that intense heat? That's your total fixed solids. And last but not least, total suspended solids, or TSS. This is just the portion of solids that gets physically trapped when you pass the water through a tiny 2 microliter filter. To complete this physical profile, we have to look at clarity, color, and heat. Turbidity measures the light-transmitting properties of water, basically how cloudy or muddy it is. That's measured in nephelometric turbidity units, or NTU for short. Next, color is precisely measured using a spectrophotometer in platinum cobalt units. And finally, temperature. Now, this isn't just about whether the water feels warm or cold. Temperature is a master parameter. It's absolutely critical because it fundamentally dictates the speed of all the chemical and biochemical reactions happening inside that water body. So we've covered the definitions, the biology, and the rigorous math you need to measure the damage. But knowing the science is really only half the battle here. With permanent stock pollutants accumulating every single day and dangerous chemical oxygen demand levels rising in waterways across the globe, like we saw in those massive India headlines earlier, the ultimate question remains. Now that we possess the exact forensic tools to track this crisis, do we actually have the collective engineering willpower to reverse this trail of water pollution before it's too late? Something to think about. Keep learning, keep analyzing, and I'll catch you in the next explainer.